3. Go.
Our experiment was the anaerobic respiration from yeast to recarbonate flat soda by Lauren Cook, Amanda Shockey, Samantha Gilbert, and Sarah Harrison. The materials we used were 3 packages of Fleischmann's Rising yeast, 700 milliliters of hot water, a stopper cork, plastic tubing, flat old soda, Dr. K, 2 1-liter Erlenmeyer flasks, 500 milliliter measuring cup, and a thermometer. Our hypothesis was if the carbon dioxide can be reclaimed from anaerobic respiration, then the yeast will recarbonate into a commercial beverage. Introduction. During this experiment, it will show the concepts of cellular respiration and fermentation in yeast. This will then be converted into flat soda into a different flask. For example, when you bake bread with yeast, carbon dioxide is produced, which forms bubbles in the dough, causing the dough to rise. The heat cools the yeast, and the bubble pockets lighten the bread. And we should do this because the impact of greenhouse gases on the environment and the atmosphere is a very serious issue. They have been linked to an increase in global warming. Carbon dioxide is hard to pinpoint how long it stays in the atmosphere because it is absorbed by the ocean and plant life. It is mainly produced by burning fossil fuels, but is also produced by solid waste and yeast. The problem occurs when more greenhouse gases, such as carbon dioxide, are made in excess.
For our first step, we created CO2 to add yeast to warm water. We waited 5 minutes for the yeast to undergo alcoholic fermentation. We warmed the water to 50 degrees Celsius. Then we added the fast-rise yeast by Fleischmann's into the water mixture. So this is our first example when we added it on the hot plate, and this is the hot water that we then added into the fast-rise yeast, and then this is when we added the yeast onto the hot plate. This then started to bubble and to start making like a different kind of texture and to start have like a bread-like smell. Step 2, we converted the carbonation of flat undrinkable soda into a VO2, which is in this example right here, into the flat soda. Next, we connected the flask. This is a stopper cork right here that we connected and with the VO2, which is a glass like silver container, into the other mixture. Then we started to see the results of our experiment, which the results were to get recarbonated soda. This flat soda then ended up becoming bubbles and started to recarbonate. You can see by the bubbles here, and within a matter of minutes, it ended up bubbling, and then by today, it would probably be up to 500 milliliters. So you can enjoy recarbonated soda now, and you can save fossil fuel energy, and you can reclaim the CO2 that will not add to the greenhouse effect gases, and save soda from being added to the water filtration. So this means that when it goes down the drain, that it will not cause any effects to happen into the global atmosphere. Step 4 is I tasted it, and we ended up creating the mixture so that the carbonated taste was a bread-like flavor, and so that we would not have to, we would know that it wasn't just flat soda anymore, it was recarbonated soda.
This is the graph for the anaerobic respiration from yeast to recarbonate soda. Here we have our time that we measured in seconds, and then over here we have the CO2, the measurement of the CO2 that was released. When we first started, we started out at 1,000. When we reached 50 seconds, we got to 2,000. And by the time that we got to 100 seconds, we went way up here to 4,500. At 150 seconds, we came up to 4,900. And at the end of the experiment, at 200 seconds, we got up to 5,000. And if we were to keep going to 250, this would be leveled out at 5,000. It's not going to go up anymore. Here we have some pictures that were taken throughout the experiment. We have the yeast bubbling up, and we have a few pictures here that show the tubing that we used from the yeast to the soda. We've got the yeast on the hot plate being heated up. I'm sorry, the water. This is the yeast that we used to put in the water. This is the soda that was used during the experiment, and this is what it looks like after it was recarbonated. So, in our conclusion, yeast can create significant CO2 to recarbonate a beverage. Further research must be done to determine how to get rid of the yeast aftertaste. This laboratory setup could be expanded to a large multi-liter container to enable CO2 reclamation on a larger scale. This process not only reduces the amount of CO2 available as greenhouse gases, it only reduces the waste of flat beverages. And as before, like we talked about, it also helps us with fossil fuel energy. The waste of the flat beverages that would normally be dumped into the water system saves fossil fuel energy and making more soda. Experiment solutions. Throughout the experiment, an error that was made results different ways from how much yeast was put into the flask during each trial. In the first trial, there was a measurement amount of 3/4 of a cup. In the second trial, the measurement amount was half a cup. This mistake made the end results for the second trial different than the first, and the consequences of error affected the numbers only by a few decimal points. I would recommend for further experimentation to make sure everything is measured out in each trial before beginning. And of course, the more trials you do, the more we can prevent errors occurring.
To conclude our experiment, I would like to mention that these mistakes were not very often missed. Any other experiment that was like this was much more in depth of the mistakes. Ours was very simple things about not even adding like 1/4 of a cup. So our experiment, just the tubes and everything, the results was actually amazing what we ended up having, and the recarbonation of our soda was actually really what we were hoping for. Like that was our conclusion, and that was what we wanted to analyze our results to end up being. So that was our experiment. Thank you.